Okay, everyone, welcome back. You made it to the second lecture of CS340 networking. So last time I gave a very high-level view of the internet. I'm going to do that kind of again today, but in more detail. We talked a little bit last time about various physical media and network access types that are used at home, although, again, we didn't get into much detail. We mentioned that it's a loosely coupled decentralized system. We'll revisit that today. We defined a protocol as a set of rules for communicating and noted that the internet has a set of standard protocols that all the participants use, and this allows different vendors and manufacturers and different software developers to create systems that work on the internet without having to have one organization that creates everything. And we talked a little bit about the history of electronic communication going back to the public switch telephone network. We talked about the old telephone network as being a network that used circuit switching, and that involves reserving an end-to-end path on the network. We'll revisit that today and show a little bit more about what that means. And we mentioned that the internet uses packet switching instead of circuit switching, where data is stored and forwarded as it moves along the path, and today we'll explain that in more detail. We also mentioned that the internet delivers data in a best effort way where delivery is not guaranteed, so it's not reliable. And we'll see some of the ways today. We'll start to see some of the ways that the applications on the internet deal with that. So in many ways, everything that we covered last time is going to be reviewed today. So, but I think it'll become a lot. Today's presentation is better than the last one, actually, in my opinion. All right, so before we go on to, the purpose of this whole first couple set of lectures is to just lay some groundwork to understand some basic topics that will let us to start moving from application layer down to the link layer. But before we do that, we need to learn a little bit about every layer and every part of the system, and that's what this introduction is doing. And one of the things I want to talk about briefly now is what is a communication link at a very high level, at a very basic level. And this is just an abstraction, but for now, when we think about a communication link, I remember last time I showed you pictures of like Ethernet cables and fiber optic cables as examples of communication links. I mentioned that radio is also another one for wireless. But just in case you don't really understand what's going on in these links, let's think about what model we should have for how these links work. Okay, so you should think of them kind of like tubes. They're bidirectional. We'll think of them as bidirectional right now. These wireless is not bidirectional. We'll talk about that later. But anyway, and they're point-to-point connections that are bidirectional and allow zeros or ones to be transmitted, or for nothing to be transmitted. In other words, the link can be idle or it can be active. There's a propagation delay associated with the link. So when the sender sends a 0 or a 1, it takes some time for it to reach the other destination, the other end, which is the destination. And you should think about the 0s and 1s as flowing, like moving at a constant rate. Like there's a certain speed with which the 0s and 1s can be added to can be pushed onto this queue. And that's the throughput. So there's a certain number of bits per second, which we describe as the bit rate that we can send 0s and 1s. And there also separately is a delay between sending the 0 and that 0 kind of like moving through the pipe until it reaches the other end. And that's the link latency. Okay, so if it's longer, the latency is going to be greater, but throughput might be the same. In other words, you could send 0s and 1s at the same rate, and depending on how long the link is, it would take longer for the first thing you sent to arrive at the other end, right? So there's propagation delay, and keep in mind that at most your propagation delay is going to be the speed of light. No information can travel faster than the speed of light. And we'll see later on in some homework assignments and stuff that actually does affect computer communication in practice. Okay, so that's a simple communication link model. So keep that in mind. Last time I showed this picture of a PSTN network, a telephone network, where we had a bunch of telephones and they were connected through a simple 4-switch network. And with that old telephone network, circuit switching is used, and what that means is that a dedicated electrical path or circuit is established for the connection. So we see this green path is being used for one call that connects two pairs, and this purple path is being used by another pair. Okay, and this, I'm highlighting here one of these channels between the two switches. It has 4 virtual channels that are available on one physical wire or link. Okay, and the way that works, we'll talk more about this at the end of the class, and I mentioned this before in the last lecture, but just to make it a little bit more clear, by showing 2 calls at the same time, what's happening here is that if time division multiplexing is being used, again, we'll define that way later in the class, but the link is, even though it's one physical link, depending on what time it is, there's a time slice, a periodic time slice associated with each of 4 different virtual channels, which I have color coded here. And this allows, for example, the green call might be using this green colored time on that link, and the purple call might be using this purple colored time. Okay, but these are dedicated. So during the duration of this call, this no other calls can use these 2 channels that are dedicated to these 2 calls. Okay, so there's a finite number of users that can be supported by a circuit switch network. In this case, across this link, there are most 4 calls that can happen, right? Now, packet switching is different because it doesn't reserve capacity on the path that's needed to send data from the sender to the receiver. It uses packets and a store and forward type of data transmission. So what's storing, by store and forward, we mean that the data that is sent from sender to receiver, this blue, these blue squares are the data, and it's actually broken into chunks, which we call packets. And the reason it's broken into packets is so that so there can be a small amount of data that it's like separately routed or transferred, let's say, from sender to receiver, and we just have to figure out how to send each of those little packets. So this first piece of the data is transferred from the source to this intermediate router, and it's transferred using that link model we talked about before, 1 bit at a time, at whatever bit rate the link supports, and then the data moves along the link, reaches the other side, and the receiver, which in this case is this intermediary router, it gradually gets the data until eventually it gets the whole packet. Right? But at that point, the data hasn't really arrived yet, because where it needs to end up is on the far right-hand side destination. So this first packet has moved 1 hop toward the destination. It has not reached the destination. This router then needs to decide which of the several links it has to forward the packet along. We'll talk about how that happens in the middle of the class, of the quarter. And then it'll store that packet here for a while until it's ready to be transferred, and then it'll move from this hop to the next hop. Okay. So with packet switching, each of these, there are many intermediate routers along the path. I mean, that's also true in the circuit switching diagram that we saw. There were many switches through which the data had to flow, and that's simply because you can't have a direct connection between every caller. That would be n squared connection links, which would be too expensive. So you have intermediate routers or switches, but with packet switching, the difference is that the data is broken into packets. The packets are stored in a queue when they reach one of these intermediate routers, and they're eventually sent further along toward the destination. So if the sender wants to send data, it doesn't have to reserve a connection, a path all the way to the endpoint. It just breaks its data into packets and sends the first packet to the next hop, and then it assumes the next hop router will do its work, which is to pass it further along the path so that eventually it reaches its final destination. Okay. This is a much more dynamic way to share the links, because these routers are doing is they have a link. So if this router has this link on the right-hand side of it that it's using to send the data from multiple users, just like with the telephone network example, except instead of having like certain time slots that are periodic that are reserved for different callers, it just looks at its queue of packets that are waiting to go and takes the one from the front of the queue and sends that. So it can kind of dynamically schedule who uses its outbound links without having to schedule those ahead of time. Okay. So I was just showing you a little bit about what a router does. These routers are what is in the core of the internet, of the network. So they're shown, this diagram here shows them in red. It shows two different classes of routers, but the core routers are shown in red, and these are the routers that are just connected to other routers. There also are some routers that are connected to edge devices, which are not core routers, but edge routers. That's not too important to understand right now. But what I want to point out just at a very high level is that what's happening, these internal routers, these routers at the core, are responsible for just forwarding traffic from other users. They're not, and they have to do that. They have there are two things that they do. They have two responsibilities. One is to figure out what the best paths are to use. So these routers have multiple connections, and when a packet comes in, it needs to make a choice of which of the several links it should use to forward that packet so that it reaches its final destination. The packet will have an IP address on it for the destination. It needs to figure out how to get to that destination. And it uses a distributed routing algorithm to figure that out. We'll talk about that at length in one of the one of the projects will cover that. And then once those distributed routing algorithms, we sometimes call that the control plane in IP. But once that's those distributed routing algorithms run and come up with solutions to the best paths, the best routes to take to reach different destinations, the routers follow those rules that were decided by the distributed routing algorithms in forwarding packets. So the main responsibility of a packet, really what the purpose of the router is to forward packets, but it needs the information from the distributed routing algorithm to decide how to forward packets. Okay. But we'll talk about this stuff in chapter 4 or 4 and 5. I forget exactly the chapter number. So it's in the middle of the class. All right. So let's come back to that picture similar to what we had before, where we have some computers that are sending data, and that the data is broken into these packets, which I'm showing as squares. And the blue squares are pieces of data coming from user A, and the orange squares are pieces of data coming from user B. And they're going through a network to reach the final destination, and in that network there are links and there are routers. And when packets arrive at a router, they're placed on a queue. So the router has some memory. It's basically a computer that has RAM. And this router wants to send packets out as fast as it can, but it's connected to links that have finite speed. So in this case, this link on the right-hand side has a bit rate of, let's say, 1.5 megabits per second. That means that the rate at which it can send packets is limited. So if it receives packets at a rate greater than that, it has to queue them up so that eventually those will get a chance to be sent on this outbound link. Okay. If the rate of packets coming in is greater than the bit rate or throughput of the outbound links that it has, then this queue will just keep getting bigger and bigger, right? And eventually, if this queue is implemented in memory, which it would be, you'll run out of memory, the queue will get full, and new packets coming in will be dropped. So one of the reasons we say that the internet is unreliable is because packets are delivered with best effort, and when we say that, one of the reasons for that is that these routers have fixed size queues, and if the queues fill up, the packets are dropped, and when a packet is dropped, the router doesn't do anything to notify the sender that data was lost. And this was an explicit design decision in the design of the internet, that they would they decided to make the network a best effort delivery network and not try to give the sender confirmation that a packet was delivered. Now, of course, your applications do require that confirmation and do require reliability. So we'll implement reliability and delivery confirmation using a protocol that works on top of the internet, which is called TCP. We'll talk a little bit about that in this lecture just to introduce it, and then we'll talk in detail in the kind of chapter 3, I think. Okay. All right, so we mentioned before the idea of latency being the time it takes for a data to reach its destination. When we're talking about the internet or an IP network, IP just means internet protocol, so an IP network and the internet are kind of almost interchangeable. There are several different sources of delay that we can model and talk about. Okay, 4 different sources of delay that I want to talk about here. So the first one, and we're just talking about one of these packets as it flows from like one of these blue packets that goes into the router. It queues up in the router and eventually is transmitted on some outbound link to the next router. Okay, each one of these hops, by hop I mean a step from between a machine, which is either a source, destination, or a router. Each one of these hops, so this is showing 2 hops. Each one of these hops has 4 different kinds of delay just on that one hop. The first is nodal processing delay. So that is when the packet arrives at the router has to examine it to figure out what it's going to do with it. It checks for bit errors and it looks at the IP address to figure out what output link it should use to send the data. This router actually has 3 links, 1, 2, 3. So when it comes in, it doesn't have to send it to this right-hand side link. It could send it down here. Like, for example, if A was sending a packet to B, if this packet had the IP address of B on it, then this router would look at the address and decide, oh, that packet has to go to the down left link instead of to the right-hand side link. Okay, so for that router to make that decision, it needs to examine the packet and look at some lookup table or something, right? So that's all that is part of the nodal processing delay, so some kind of processing that the router has to do when it examines the packet. The second source of delay also occurs on that node, and that is the queuing delay. Even before the router looks at the packet might sit in some kind of queue waiting to be processed. We'll see later on in the class that there are actually, if you really want to look at the details, there are several different queues that are probably built into a router, but just for a first approximation, let's just consider there's one queue. Packets come in, they go in the queue, and they wait. The amount of time they wait depends on whether there's an imbalance of inbound traffic and outbound traffic. In other words, whether a lot of traffic arrived that has not had a chance to be sent yet. Okay. It depends on the congestion level of the outbound link. If the outbound link is not very highly utilized, then all the incoming packets will be sent immediately because that outbound link is generally available. Okay. The 2 other sources of delay are associated with the links themselves, and I mentioned these earlier when we talked about the link model. One is the transmission delay, which is transmission delay means the amount of time it takes to transmit that packet. So that's kind of right here. I'm showing transmission here. So this router starts at the beginning of the packet, starts sending the 0s and 1s of the packet. Eventually, it reaches the end of the packet. It has to send those bits one at a time, and the link bandwidth, like the bit rate of the link, determines how fast those 0s and 1s can be sent. If you take the packet size and divide it by the link bandwidth, you get the transmission delay for that packet. The other delay is the propagation delay of the link, and that is once you energize the 0s and 1s on one end, how long does it take for them to reach the other end? Okay, and that's determined by the length of the link and the speed of light if it's a fiber optic transmission, or even if it's an electrical transmission, then it would be upper bounded by the speed of light, but also be influenced by the kind of capacitance and resistance of the wire, which is just a low-level electrical detail. Okay, so 4 different delays that all add up to determine your the nodal processing delay, the delay of just that one hop. Each of the hops along the path will have a different nodal processing delay, because each of these four factors actually could be different for the different routers along the path, right? And if you're not convinced of that, I would encourage you to stop the video and just think about it, review the definitions of these delays, and figure out why each of the routers, each of the hops could have a different value for each one of those. Okay, so I mentioned in the first lecture that the internet is a network of networks, and that it's a distributed system where there's no one entity that decides what links should be built and who should connect to whom. Those decisions of what links are built and where they connect are actually driven by the business interests and the sort of selfish interests of the different participants on the network, the different autonomous systems, whether they are telecommunications companies or universities or companies like Amazon or Google or Facebook that operate their own data centers. All of those organizations build links, connect to other peers to create the internet. Okay. But before we get there, let's think about a situation where we have a bunch of networks. Let's say these are university campuses. We want to build an internet that connects all the universities in the world. Okay. Every university has an IT staff that will build the wires that connect its campus, like its users, and it'll install switches and routers to connect everyone on campus. So imagine every campus has its own local network that the IT staff manages. But if they want to connect to each other to create an internet, how should they be connected? How should all the universities connect to each other? I'm calling those ISPs in this slide, but maybe I think it's a little bit easier to think about them as university networks, because then you don't have to worry about customers and who's paying whom. If these are all universities, how should they connect to each other to create a worldwide network? So I want you to stop and think about that. So pause the video and think about it. Okay, so hopefully you've thought about that. I'm going to go through a few different possibilities. The first one is for them to connect to whomever they want to talk to. So, for example, if researchers at Northwestern want to communicate data with researchers at Argonne National Labs and University of Chicago and let's say MIT, those three places, then the Northwestern IT staff would have to make sure that there were wires that were built from Northwestern to all three of those places, right? Argonne, U Chicago, and MIT. And that would be fine and that would provide access to those three destinations, but it would not provide access to all the other universities in the world. And when a new customer it wouldn't be an internet, it would be a subnetwork. You wouldn't be connected to everyone. You would only be connected to a few people you wanted to. If you wanted to be connected to everyone and you wanted to make direct connections, you could do that. And this picture shows that. It's like a complete graph where every campus is connected to every other campus by a wire that's built, a link that's built. That's simple, but it's really expensive because they're n-squared connections, and some of them are very long. Like for Northwestern to connect to MIT, then a wire would have to be built from Evanston to Boston, right? That's very far. So you don't want to connect them pairwise. Somehow this is inefficient. You want to do some sharing, I guess. Like you want to create a network actually instead of just a complete graph. Okay, and the simplest idea for that, and actually the most efficient in some sense, would be to just say, okay, I have all of these locations around the world, all these universities that want to be connected. I know where they are, right? So let me draw on paper, like if I have that map and I see where everyone is located, let me figure out what the optimal set of edges there are that I can draw that would connect everyone as efficiently as possible. And that network, those lines I'm drawing, would be a global interconnect, or global ISP. ISP stands for Internet Service Provider. In other words, I'm building a network, a mesh of routers and links that everyone can connect to, that has sharing. So that if Northwestern is communicating to MIT, it might be using a link between Chicago and I don't know, like Detroit, let's say, that others are using to reach New York City instead of Boston and whatnot, right? So that's a way to create a much more efficient set of interconnections. But there's some downsides to that. The main one is the amount of centralized planning and control that this requires. Like, everyone needs to agree. Like, one organization needs to decide where to build those links and who to connect to. And by doing that, they can do it very efficiently, but everyone has to agree to use that one internet service provider. And in practice, that would not happen, because if these are businesses, if the provider of the network is a company that's trying to make money and provide service in exchange for fees, then presumably other companies would also want to try to provide the same service, and maybe at a slightly lower cost, and they'd be competing for the same business. So this business of interconnecting different universities, let's say, that interconnection business could be done by many different companies, and they would all be competing, right? And also, there are different parts of the world where people speak different languages, they have different business customs, there's different government regulations. So it would be unrealistic to think that a single company or organization would be responsible for building the network in the United States and also in Europe and also in all parts of Asia. It's unrealistic, right? In reality, you'd expect different organizations to be building the networks in all those different geographic locations. Okay, but when that happens, that allows different subsets of these universities to be connected, these different access networks to be connected. And again, I'm using the word university, but these could be not just universities, but companies that are providing access to customers in a neighborhood, or businesses in a neighborhood. Those are all access networks. But the problem here with this diagram, when we've introduced competition, is that now we have 3 internets instead of 1 internet, right? Like, these universities in the lower left can't communicate with the ones on top because they're not interconnected. So solution to this, what has come about, is yes, there is competition among different internet service providers to provide interconnection between networks, but there also is cooperation between them. So these red links are peering links. So these different internets, Tier 1 ISPs, they're called. Tier 1 ISP is a internet service provider that connects access networks or connects other internet service providers, that has huge networks that span countries or continents or around the world. Okay, so in order for company A and company B to provide better service to their customers, they would have an incentive to interconnect with each other. So that, let's say, Northwestern has access not to just these Midwestern universities, but also has access to East Coast universities and universities in Asia or wherever else. So these internet service providers have a incentive to build interconnections between them, peering links. And an interesting thing about these is that they're often settlement free. What it means is these two companies, A and B, might decide they're going to create a link that connects them to each other. They won't pay each other a monthly fee for the connection because they each benefit. They'll each share the cost, perhaps, of building that link, like the physical wire and the equipment that the wire is connected to. They'll share that cost, but then on an ongoing basis, they don't send each other a bill in the same way that this Tier 1 ISP might charge, let's say, Northwestern for Northwestern's access to the ISP. And the reason they don't pay each other is because they're so big that by providing interconnection, they're not just sending traffic, but they're also receiving traffic. So in some sense, each of these companies, each of these Tier 1 ISPs, A, B, and C, are like they are a big part of the internet. So they're not just when a connection is made here, it's like making the internet stronger instead of providing one organization or company with access to the broader internet. Because there are a lot of ISPs that want to interconnect with each other, there are buildings or facilities called Internet Exchange Points, IXPs, that are locations where many different ISPs have equipment and where it's convenient for them to interconnect to each other. So, for example, in Chicago, there's a IXP on Cermak Road, I think, and there may be more than one of these, actually, because Chicago is such an important geographic location, where it's one building where that many different ISPs have routers, and it allows them to connect to other ISPs with very short cables because they're all in the same building, essentially. They don't have to build long new wires to do that. Okay. So in addition to these internet service providers whose job is to connect different customers to the wider internet, there also, especially nowadays, are content providers that have come into the business of building the backbone of the internet. We call these tier one links, these internal links on the internet that connect a lot of different users. We often call that the backbone of the internet because they're really high speed wires that travel over long distances that carry a lot of data. The big tech companies like Google, Amazon, and some other companies you may not have heard of, like Akamai, that are in the business of selling content delivery network services. These companies, although they're not in the business of selling internet access exactly, like Google, for example, doesn't sell internet access, but it is in the business of providing search and mail and YouTube and all that stuff to customers around the world. In order to make their services faster to customers around the world, they have actually built their own global network to connect their data centers around the world so that they can move their own data around the world as quickly as possible, and so that customers can more quickly access their data. So Google's global network is interconnected with various ISPs around the world, and so you as a customer, or let's say a client on Northwestern's campus, you might access from Northwestern's campus, you might go to a tier 1 ISP, and that ISP might be directly connected to Google, and then a Google router that might connect to a different Google router in a different part of the world, and then that's where you might get your mail, let's say, from. Okay. There also are other networks that are not quite as big as tier 1 ISPs that still are interconnected with other ISPs, but they might have to actually pay for that access because they're not big enough for the tier 1 ISP to think it's worthwhile to share the cost of the link. Okay. So if we look at the core internet structure, we have tier 1 ISPs and content providers. So I'm listing Google here just as an example. Google's not the only one. It also includes companies like Facebook and Amazon. These tier 1 ISPs are the organizations that have links across oceans and across continents. There are internet exchange points, which are buildings that multiple different ISPs are connected to, so that in one building, many different ISPs can interconnect with each other. There also are regional ISPs that have links that might cover a relatively small geographic region. And then there are access ISPs. The access ISPs are the companies that provide access to individuals. So if you are getting internet access at your home, whether it's through cable or DSL or on a cellular phone, those companies are connected to other ISPs. They could be connected to a tier 1 ISP or a regional ISP, or they could be a tier 1 ISP. Like if you're using Verizon for your cellular service. Like Verizon's a big telecommunications company that is a tier 1 ISP in a sense. So these different labels are not totally distinct. Like there's a little bit of blurring, and these terms are not totally different. Some of these tier 1 commercial ISPs are huge companies that have networks that span the world, but you may not have ever heard of them. Like CenturyLink is a company that has fiber optic links that cover the world, that go across oceans and whatnot. And of course, different countries have different tier 1 ISPs. Like China Telecom is a big one in China, of course, but not here. And same thing for AT&T. Operates primarily in the U.S. Yeah. Okay. Now I want to go through a little fun experiment to talk a little about the economics of how the internet grows, and the kind of the advantage of the internet being decentralized, and how that leads to it improving and I guess growing in a natural way. Okay, so this is just an illustration. This is not a real network, but let's imagine that the internet backbone is as drawn here with the red links. So these red links represent big fiber optic cables that provide a large amount of bandwidth between these dots, which are routers. And of course, these there would be different customers connected to these dots. Maybe you can think of these dots as universities that wanted to be connected to each other, but they could also be like local telephone companies and stuff like that. So this is the backbone. So if their customer in Argentina wants to fetch data from a website in India, then that data has to flow along this backbone, right? So it has to go like either in this direction across the Pacific, or across the Atlantic in this direction, right? Okay, so that's fine. All these nodes are connected to each other, but some are better connected than others. So for example, previously Miami and San Francisco were connected, but not well connected, because the number of hops between them and the physical distance was pretty high. So it used to take 1, 2, 3, 4 hops to get between San Francisco and Miami. That means that when customers in those locations are trying to access, like if you're a customer in Miami and you're trying to access, like, I don't know, let's say Gmail, and let's say that Gmail is that's Google, and let's say that all of Google's data is in California. In reality, it's not all in California, but let's just say it is. And that means that you have to travel 4 hops, so then your Gmail experience is kind of slow, right? So theoretically, this could be improved by building a new link. So this yellow link here shows a plan to build a link between San Francisco directly to Miami, and that would improve the internet, right? Because now there would be the option to go directly from Miami to San Francisco. The number of hops would be fewer. And remember that I talked about those 4 different delays associated with a node, and 2 of them are associated with just the queuing and processing on the routers. So the fact that it's fewer hops really does make it faster. The physical distance also matters, and there also is less physical distance here, about maybe half as much distance as going all the way up to New York first, right? So now what I want you to think about here is why this link would be built. So we can see that that provides a benefit, but who does it provide a benefit to? And that will let us understand who might actually pay for this link to be built, and who might go out and actually build it. Now, for people in Miami, like the customers in Miami, this link provides faster access to San Francisco, but it also provides faster access to Japan, right? Because previously, whenever we wanted to go to Japan, we had to go up through New York. So we can use this link as a shortcut to all of Asia. It reduces the number of hops to reach all of Asia by 3. And that's so for Miami, and also reduces the number of hops to South America. You can't see that because it's covered. But the Miami customers, and also to a lesser extent the Georgia customers here in Atlanta, these customers are all benefiting from this link. Like their access to roughly 1/3 of the world has become shorter by about 3 hops because this one link was built. Okay, they used to be at the end of like a dead end. Now they're more in the center of the network. Okay. On the flip side, anyone in the world who wants most anyone in the world who wants to reach Miami benefits. About half the people. Those who are reaching Miami from the left-hand side can get there more directly through San Francisco rather than going through New York. That's nice, but Miami is only a small part of the internet, so it doesn't affect very many people. For example, for the ISP operating in San Francisco, building this link provides faster access to Miami and also faster access to Atlanta, but that's it, actually. For Miami, it provides faster access to about half the world. So this link is beneficial, but it's primarily beneficial to Miami. So this ISP that operates in Miami would be the one who has the incentive to build this link. So if this link was going to be built, we can expect that the cost of building that link would be paid by the ISP in Miami. Okay. What about this Tokyo to Sydney link? So I want you to stop and think about this and think specifically about, is there a benefit to building this? And also, who would pay for building it? And when would they pay for building it? So stop and think about that. Okay, I hope you thought a bit about this Tokyo to Sydney link, and I think what you'll find is that it's a similar situation where you have a dead end, which is Australia, that's now put more in the center of the network. So these customers in Australia now have much faster access. With this link, they have faster access not just to Japan, but also to northern China, but also to all of the Western Hemisphere, like the United States and South America. Previously, these Australian customers had to go through Indonesia and China every time they wanted to reach the United States. Now they can go more directly through Japan. Okay, so this link provides a big benefit to Australia. To Japan and like China, it provides faster access to Australia, but only to Australia. So really the majority of the benefit is for the Australian customers in Sydney. So if this was going to be built, it would be built by probably the Australians. Okay? And they would build it if the number of customers in Australia was enough to, and the amount of benefit seen by those customers in Australia was enough to pay for the cost of this link, basically, right? Okay. Assuming that markets work efficiently. All right, so we got one other example. How about we add a link from Johannesburg, South Africa to Antarctica, right? So stop and think about that. Does it provide a benefit? To whom does it provide benefit? And who would pay for it? And would it get built? Okay, or when would it get built? Okay, stop and think about that. So the answer here is similar, I guess. The analysis is similar in that we have a dead end. We've actually extended the network. So previously, the internet did not cover Antarctica. And if these Antarctics researchers or penguins or whoever's down here wants to talk to the rest of the world, they have to do it with another technology, like maybe satellite radio or something. By doing this, so it's good in a sense because it provides more access, but that benefit is seen only by a few people, like the maybe 30 people who live in Antarctica, or 50 people, whatever it is, very small number. So the cost of this cable is going to be pretty high. It's a very long cable. It's in rough seas. But that cost is going to have to be split by these 30 people plus whatever people around the world want to talk to those 30 people, which is pretty small, right? So it's unlikely this link would be built until the demand in Antarctica gets to be very high, right? Or, I mean, if those 30 customers happen to have a lot of money to spend, for example, if they're scientific researchers that have a lot of data that's very important that they send, maybe it's okay that the internet connections cost $10,000 per person to pay for this link. Okay. Now, we saw on that map that a lot of the backbone crosses oceans, right? Okay, so there are undersea internet cables. So these are cables that just are like sitting in the bottom of the ocean that are fiber optic cables. They're bundles of fiber optic cables. That's occasionally they malfunction and break, and that's why we have more than one of them. But what's interesting now is that I talked before about how content providers like Microsoft, Google, Facebook, Amazon, these big tech companies, they are increasingly building their own backbone, they're increasingly becoming the internet because they provide so much of the data. It's so important for them to have fast access to their customers. You can see this plot shows the share of the undersea bandwidth that now, well, 2 years ago, or in 2018, was operated by content providers. It used to be that if you look back to the early days of the internet, that everything was internet backbone here really refers to public internet. So this is like internet service providers. This fiber optic cabling that's being laid by companies like Microsoft and Google is in many cases that's not really part of the internet, but it's those are just internal networks that those companies can use to transfer data between their own servers, right? That's why it's not labeled as an internet backbone. And there actually are a couple of different visualizations you can check out. So I would encourage you to download the PDF of this and click these links, and I'll show you one of them, submarinecablemap.com. That shows you can actually browse the undersea internet cables, and you can see like where they are and who operates them. So if you click one of them, it tells you a bit about it, like when it was created and who owns it, the length. So it's pretty cool, and you can see exactly where they are. And you can see, I think, yeah, it looks like there still are not any links to Antarctica, unfortunately, for all those penguins. They still don't have Facebook down there. All right, so this is the intermission. This is a good time to take a break. I'm going to resume the recording in a minute. You'll see it immediately. But if you want a breather, now would be a good time to take it. Okay, and we're back. So I was just talking about the internet core and routers and what they do and how this kind of multi-hop routing works, and also how the internet evolves by links building up sort of based on market forces in the network. Now I'm going to spend a few slides talking about another like high-level principle of the internet, of the protocols of the internet, and specifically how the network is designed, or the protocols are designed. The operation of the network is designed in layers from a software perspective. Functionally, it's layered. Okay, there are many different things. There are many different things that have to many different problems to solve in networking, and these are solved by dividing them into buckets and different protocols solving the different classes of problems, and they kind of build on each other. And they built historically, and they also build kind of technically with, as we'll see in this lecture. So if we're talking about the World Wide Web, and it's like visiting websites. There are several protocols involved in getting those website requests to work in a browser. So at the highest level, there's HTTP, which is the Hypertext Transport Protocol. Next lecture, we'll talk in detail about what that is when we talk about application layer protocols. But this is like a protocol for browsers to make requests for pages and images, and basically for clients and servers to interact. So the client's the browser, the server's the web server that's some company that wants to provide you with data, usually. This handles things like URLs, redirection, caching, proxies, and cookies. Lots of things. Basically, all the things a browser needs to complete its functions are handled by this HTTP protocol. But this protocol is built on top of several other protocols, and they move from a high level down. In this class, we're going to be exploring protocols from the top down, in this sense, from application layer down to like the very bottom. We have like almost physical concerns of networking. So right below the application layer, we have TLS, which is used for, it stands for Transport Layer Security, but basically it's for encryption and for security. This is optional, but it's pretty much universal nowadays. We'll talk about this actually at the end of the class. Below that, we have TCP, Transmission Control Protocol, which is a way to provide an application with a reliable stream of data instead of having to deal with individual packets that might individually be lost and be reordered and all that stuff. Excuse me, and I'll talk more about that in this lecture. Below that, we have IP, Internet Protocol, which handles getting packets to their destination across many hops. So this is a challenge in itself because we have all these routers that don't necessarily know about all the other ones in the world. They have to figure out, okay, if I want to get a certain packet to a destination, any destination on the internet, I have to figure out which direction to send it in, right? To send it like one hop toward the destination. IP protocols and BGP handle that. And below that, we have a variety of protocols like Ethernet and Wi-Fi and others that are used for handling a link. So if we have a link with two devices or more than two devices are sharing this link to communicate what could be the radio spectrum that many wireless participants are sharing. It could be just a wire that has two participants on either end of it. It could be a Ethernet subnet, which we'll talk about near the end of the class. Anyway, but there's some details about kind of those low-level concerns of sharing a link with two or more participants. Okay, well, those are all different protocols and different layers, and we can talk about them separately as long as we have an abstraction of what comes below it, I guess. So the way these different protocols build on each other, everything still happens in packets, but we have sort of packets within packets, and every layer adds an additional packet out to enclose an inner packet. Okay, and every packet has a header, which is the beginning part of the packet that has information related to that particular protocol. Okay, and I'll show you this in more detail in a few minutes when I look at an example. But so before Ethernet was at the bottom, this is like for handling a link, an Ethernet link in particular. There's a header for that, and there's a payload for the data you want to send. But then that data is an IP packet, which is that next higher up level in the protocol stack. And here, so that the payload here is a IP packet that includes IP headers, which are things like IP addresses and other stuff, and then an IP payload, which is the data you want to send. But that data is not just data, but it's a TCP packet. I mean, technically, these usually terms other than packet are used. I like to just call them all packets. Like Ethernet frames, IP packets, and TCP segments would be the way some people describe them. I like to call them all packets. Anyway, this TCP protocol is responsible for breaking a stream into multiple packets and like assigning them all like numbers. Those are sequence numbers, and acknowledgments for confirming that packets arrived so that we don't lose packets, things like that. We'll talk about the details later in the class. But then inside that, we have another layer of protocols. In this case, we're using HTTP to have a web browser request a page from a website. Okay, and there are headers for that, and then there's the data itself. So the data we're fetching in this connection is an HTML document. You can see at the very bottom what that is. That HTML document is split across multiple packets, and each one of those packets has headers at the beginning, and it has multiple types of headers associated with the different layers of the networking stack that solve different problems that are important for networking. So the end part of the headers, these HTTP headers, all are used by like the browser and the web server to get their work done of fetching documents. These yellow headers for TCP are all associated with the reordering of packets and the loss of packets that might need to be retransmission. So there are values in here to help with that process work. Above that, we have the IP header that has things like IP addresses, so that packets can figure out what their destination is across the worldwide network. And then above that, we have things like in the Ethernet headers. We have details that are just associated with a single link, like MAC addresses. So this actually would change every time the packet goes across a new hop. This Ethernet packet gets removed and a new one gets re-added because you have a new link. But we'll talk. This is a summary of like almost everything we're going to cover in this class. So you're not going to understand all this now, and there are a lot of acronyms here that you're not necessarily going to understand. But I want to give this picture of the packet being the unit of data we're sending. There being headers at the beginning that are used by the protocols to solve the various networking problems, and then at the very end there's data, and you have packets within packets, and headers associated with the different layers of the networking stack. Okay. So there's a program called Wireshark that you're going to be using in homeworks and also probably in your projects as well to debug them, that you can use to observe network traffic, and it's pretty cool. So here is Wireshark running on my machine. So you can start a capture, and it'll actually just capture packets until you tell it to stop, and it lists out all the packets individually, and you can see the source and destination IP addresses. You can see what protocol is being used, and then you can see details down the bottom as you click each one. So this is kind of a summary view, and if you click one, you can see more details. For example, this, let's pick one that might be relatively easy to interpret. This one here, so when I click this packet here, you can see where it came from and where it went to, source and destination. So this is my laptop is 192.168.0.213. This destination 34.95.111 is somewhere out on the internet. And the bits that were sent are actually shown down here. These it's shown in hexadecimal, but these are the bits of the packet encoded in hex. On the right hand side is the ASCII encoding, which doesn't make any sense because this is not a human readable protocol. But as you in this middle view, you can click on different layers, different protocols to see how they're encoded in the packet. So the Ethernet headers, if you click Ethernet, you'll see highlighted in blue on the bottom is the beginning part of the packet that's associated with Ethernet. After that is a segment that's associated with IP. These are still headers, and then there are finally some PCP headers. And actually, this packet doesn't have any payload. It's all just headers. So because it's it's probably just a TCP acknowledgement, or it's part of a TCP handshake, which we'll talk about that in a few weeks. So don't worry about that yet. But this is a program you can use to see what's going on in your network. You can see your own traffic. You also might be able to see other people's traffic if you're on Wi-Fi or something like that. Okay. All right. So another networking concept that we'll need to get started in the application layer chapter, so the next chapter, and for you to get started with the first project, we need to understand what sockets are. Sockets are going to be the abstraction of a network connection that we use to build applications. Okay. We'll talk later on about how sockets are implemented, but for now we're going to assume, as a programmer, we can ask the OS for a socket, and a socket is a network connection, basically. It's essentially a combination of an IP address and a port number. So what is a port? Okay, so we know that I mentioned briefly that every computer on the internet has a unique IP address. So an IP address is a number that indicates which computer you are on the internet. So if we want to make a connection to someone else, we need to know their IP address. That's not enough, though, because we want to be able to build a system where machines can have many network connections at the same time. So in other words, if I connect to a server or want to have one machine connected to multiple websites, if I just use the IP address to identify that connection, that's not enough because it doesn't distinguish between all the different programs running and all the different network connections that are running that should be able to run at the same time on that computer. So sockets have port numbers. So these are 16-bit numbers. So in other words, these are integers between 0 and 64,000, right? No, 16,000. No, 64,000. That distinguish different connections. So your computer can have 64,000 different network connections operating at the same time, as long as each one has a different port number. And they're all sharing the same IP address. And what these port numbers do is allow the operating system to distinguish between network packets that arrive and figure out which of the many programs are running should get that data, should get that packet. Okay. So if I have multiple tabs open, then I can send a request, get a response, and then the OS, the operating system is what manages the hardware. So the operating system will get the packet, and it can decide which of the several programs running should receive that data. Okay. There are both TCP and UDP sockets. We'll talk about what the difference is later. Let's ignore that for right now. But for now, just think of a socket as a network connection that was created by a program, and you're going to write a program in the first project to use sockets to make network connections without yet really understanding what's going on at the low levels. We're just going to be operating at a high level with sockets. We just have to specify the IP address we want to connect to and the port number we want to connect to. And there are port numbers used on both on both sides of the connection. So both the sender and receiver, I guess you could think of, both have port numbers. They could be the same or they could be different. And there are different services sometimes are assigned port numbers by convention. So HTTP is the protocol used by to fetch the browsers used to fetch documents from web servers, and for a web server to use HTTP, it should listen on port 80 because that is by convention the port that you'll connect to fetch a web page. So if I just type google.com in my browser, DNS, we'll talk about DNS later, but DNS will translate google.com into an IP address. So we'll get that IP address. Now we know what computer we want to connect to. We don't yet know the port number because we do need a port number to make a network connection. But because we are using a web browser, the browser knows that, okay, we're using HTTP as the protocol, and therefore, by convention, the port number we should use is port 80. So it'll use port 80. It'll connect to port 80 on the server. Okay. And there are other standard port numbers used for standard services that are listed here. Okay. If you use an encrypted web connection, that uses port 443. Email uses port 25, and so on. Okay. Now, I said that web servers use port 80 by default, but there are ways to override that and to use custom port numbers for web servers. And the way you do that, you may have seen once in a while in a URL, after the host name, a colon and then a number. And that colon and number specifies a custom port number. So the standard URL here, this is specifying a server that you can use for this class to run your code. If you just specify this URL, it'll connect to port 80 on that machine. So it'll look for software running on that machine that is listening on port 80. But if you use one of these other URLs, it'll connect to a different program. It'll look for a program that's listening on port 8000 or 8001 or 8002. And this would allow, for example, multiple students who are using that same machine to all be running web servers. They're all listening for connections. They're all reachable, but they're reachable at different port numbers. Okay, you can't reuse the same port number. You cannot have two programs listening for connections on the same port number, because then the OS, when it got a packet, it wouldn't know which program to give the data to. Okay. So that kind of showed how you can have multiple web servers running on the same machine. Now, those would be kind of hard to reach because you have to use these weird URLs with port numbers. But for the purposes of, let's say, testing out your homework assignment, you can use these kind of URLs with no problem. We also have clients make multiple connections and multiple web connections at the same time. And we also enable that by using different port numbers. Okay, but those are different port numbers on the client side as opposed to the server side. Okay, so imagine the common situation where you have multiple tabs open in your favorite browser, whether it's Chrome or Firefox or Safari or Edge or whatever. Those programs are going to make requests to fetch documents from web servers, and then data is going to come back. That data is going to end up going to the OS, and the OS needs to hand that data back to the appropriate process or program. Somehow the data has to end up at the right tab. You can imagine each of those tabs is like a different program, or it's a different thread in a program, but you can think of them as different programs. The way you can make this work is by using different source ports for each outbound connection. So if this blue table is showing one computer, this computer is actually running two browsers at the same time, and each of those browsers has has two tabs. Those each might make connections to fetch pages, and you might be fetching 4 different pages at the same time on those 4 different tabs. The socket that you use for those, which is in other words the connection that you make, is going to use the same have the same IP address for the source, like because there's one computer, your laptop, which is the source of those 4 different connections. The IP address is the same, but the port number is different. So this combination specifies the origin of the data for this connection and the other connection, the other one, and these are all different port numbers. The destination could be the same or different depending on whether you're visiting the same website or a different website. This example shows 3 tabs visiting one website, the same website, and a 4th tab visiting a different website. And you'll notice that they actually are all connecting, the first 3 are connecting to the same destination IP address and port number. But because the source IP address and port is different, because these 4 are combined are different, it's a different connection. It's okay if the destination IP address and destination port are the same. Yeah. Now, when data comes back, your laptop's operating system will get a packet from those 2 servers that you contacted, right? Here's some examples. And it's showing the remote port number, the remote IP address, and the destination IP address and port number for those packets that come in. Now, I want you to stop and think about each of these 4 and tell me which of the tabs would get each of these 4 packets, the data that's in each of these 4 packets, okay? So tell me what browser tab should be in these question mark areas. All right, I hope you stopped and thought about that. The answers are shown here. All you have to do is match up the port number and destination IP address with what was the connection that was established on the outbound side. This last one actually doesn't match anything. So data came in from this web server to our machine, and the destination port was 21111, but that does not match any of the outbound source ports, so that data is actually dropped. There's no program who's listening for that data. Okay. As a side note, these port numbers, those below the number 1024 are privileged. These are the ones that are usually assigned to specific protocols, and usually you have to be administrator or root user on a machine in order to listen on those port numbers. So if you were using one of the shared Northwestern servers and you wanted to run a web server, you can run a web server, but only on ports that are above 1024. This prevents like any user who doesn't have root access from running official looking web servers or mail servers or whatever on a machine. Okay. One other thing you may have noticed is that sometimes unusual port numbers are used to hide configuration pages. Like if you have a device like maybe a router, a home router, or another kind of appliance like a voice over IP telephone or something that can be configured through a web interface, sometimes they will use weird port numbers above 1024 that look kind of random. And this is just kind of a very hacky way of providing a little bit of protection so that you would have to know the right port number. You have to know more than just the IP address of the device in order to connect to the web server for configuration on that machine. I mean, you should also have a password or something to protect it, but it just provides a little bit of obscurity, I guess, for the service. Okay. So we mentioned in last lecture, the first lecture, that the internet is a network where we send packets of data. It's a packet switch network. We can think of sending data as sending postcards. We have to break our data into these little chunks of small size, and they each are sent individually. They could arrive at different times. We're not guaranteed that they're going to be delivered because the queues might be full or links might break or something. That's really inconvenient, right? If you're a software engineer and you want to make a connection to send data to another machine, you don't want to have to worry about breaking up your data into pieces and worrying about it being reordered and pieces being dropped. You want to have a reliable streaming connection to that other machine. And there's a protocol called TCP, which gives a reliable bidirectional stream of data for applications to use. It gives the illusion of a bidirectional pipe for data. So for thinking about analogies, the internet itself in reality is like sending postcards, but TCP gives us the illusion of a reliable bidirectional pipe. And the reason why we think of it as a pipe is because the ordering is maintained. Like if we send things 1, 2, 3, 4, if send data 1, 2, 3, 4, it'll arrive 1, 2, 3, 4 in that order. And if 2 was dropped, then it'll somehow be retransmitted and reassembled on the other end in the right order. Okay, and the way TCP works is complicated, but if you just add we'll have to spend at least a week or so talking about it, if not 2 weeks, I forget exactly. It's one of the most important protocols on the internet because it solves multiple different problems. But just at a high level, you can think intuitively about how you would build reliable transport, a reliable connection when you have these unreliable and reorderable packets. One thing you need to do is figure out a way to break your message into multiple small packets. That's called message fragmentation. And you need to maybe assign a number to each one of them so that you know what order they should be received in, or if they arrive out of order, you can look at the numbers to reassemble them in the right order. You need some kind of delivery confirmation and retransmission. So if a packet's lost, you end up retransmitting it so that you can actually get all the data on the other end. Those are the obvious things. You also need flow control and congestion control so that the pacing is right, but that's a little bit more subtle, and we'll talk about that later. But the main things you need are like some way to get things in the right order and to retransmit things if they're lost. Okay, that's what TCP provides. TCP also provides port numbers so that you can have multiple connections between a given machine and the rest of the world. It's not always used, although it solves important problems. There are a few rare cases when you don't use TCP and instead use an alternative, which is called UDP, User Datagram Protocol, I think. And so in that case, you have to manually break your data into little packets. You have to manually, you have no guarantee that they're going to be delivered. You don't have any guarantee about the ordering. But the advantage of UDP is that you don't have to. It's less work and it's faster because you don't have to do a handshake at the beginning to get set up. This previous slide that I kind of blew past showed that at the beginning of a TCP connection, you have to do a handshake where you send packets back and forth to establish some parameters before you get started. And that's UDP avoids that if you don't need all this reliability. Okay, I just mentioned that UDP is a simpler alternative to TCP. It basically is just like these postcards that could be dropped. The only thing UDP adds that isn't already available in the lower level IP protocol is port numbers. So you can have multiple connections that are sending these postcards, and they can be associated with different programs. There are a few applications that do use UDP, even though it's unreliable, even though packets can be reordered. It doesn't have, and that size is limited. Usually it's for media streaming, where if a packet is lost, retransmitting it doesn't make sense because it's going to be out of date and useless anyway. But we'll talk more about UDP and TCP in Chapter 3. Okay. So I tried to give a little bit of an overview in this second lecture about what protocol layering is, why it's important. We're going to talk in the next lecture about application layer protocols, including HTTP, and then we're going to keep moving down the stack to TCP, then IP, and then link layer things, including Ethernet. And to get down to this outside layer, this lower layer, is going to take the whole quarter. Okay, so we're going to spend a lot of time at each layer. But hopefully right now you have a little bit of an approximation of what TCP provides as far as a socket, this pipe. Think of a pipe, bidirectional, reliable connection. We know, I said the internet itself is not reliable, but somehow TCP and the protocols below it give you the illusion of reliability by implementing retransmissions and reordering corrections and things like that. Okay. So, and in this lecture, just to recap, we showed how the network is comprised of many hops and how packets are transmitted in a store and forward way, and there are queues at every router that if they get filled up, packets are dropped. There are 4 kinds of delay that can happen at each hop. Nodal processing and queuing are associated with the router, and transmission and propagation delays are associated with the link. And this is kind of added up for every single hop. We showed a little bit about the economics of the internet, I guess, how it's a network of network, and how peering happens, how it grows, how we have tier 1 ISPs and big content providers have these build these high-speed backbound links, and more of them are added over time if there's a demand for them, and the costs are associated with whoever are paid by whoever benefits. And that's because people do benefit when new links are built. They have been built, and the internet has gotten faster and faster and more densely connected. I showed how networking uses layered protocols like Ethernet, IP, TCP, TLS, and HTTP are examples that are kind of independent but build on top of each other. And when you're writing software that uses a network, you have an abstraction of a network connection that's called a socket, and you have to choose between either TCP or UDP sockets, but mainly we're going to be looking at TCP sockets because they provide a lot more than UDP. They provide reliable bidirectional streams, which where you don't have to worry about like the size limits of packets. You don't have to worry about reordering. You don't have to worry about packets being lost. Somehow the TCP protocol handles that stuff for you. Port numbers are these things that distinguish between different connections you have on a computer. And if you want to listen for connections, you have to choose what port number you want to listen to. If you want to make a connection, you have to specify what port number you want to connect to, in addition to the IP address. Okay, so that was it. Again, it's a lot of information, but I hope that was useful.